Okay, so we're continuing our talk on missing data in longitudinal studies, and this is very important topic. Like, probably one of the most important topics. Obviously, we learn about the models themselves, like linear mixed models, generalized linear mixed models. But in terms of um, what I think is important in the class, I think this is something that's very important. It's something that I've been developing material on as the years have gone on, and so a lot of this is kind of recently been developed, um, and it's something that I think you guys, some of you, maybe three or four at least, may be able to apply for your project. Okay, so some of you have already mentioned to me that you have, missing data. What makes your data set messy? Well, subjects may drop out. You may have missing data. And so I really would like to see you guys apply some of the methods that we're going to talk about today. We already went through the first part of this. So quickly, I'll just kind of review what we talked about. If we have some outcome that we've measured on subjects, and this is probably something that would never happen, but it just kind of gives you an appreciation of how mixed models work and how it's, in a way, it can account for missing data if you have assumed the right structure for the data. So if you have 7 subjects and you measure some outcome on them, but you only follow up on actually 8 subjects. You start with 8 and then 3 drop out. So you only have 5 subjects that stayed in for visit 2. But if you've lost the information about how subjects are attached, subject 1, subject 2, how are they connected, with the spaghetti plot, if you've lost that, then what's your best guess on the overall average change? Well, you would just take the average at time 1, the average at time 2, and connect them. But if we were to have more information about actually what happened, and now we see that it was the subjects that started lower were the ones that dropped out, by putting in a random intercept in your model, our predicted values are actually going to look as they should. Now, the researcher, if they didn't know, they didn't see the information on the 3 subjects that were lower, right? We have a perspective that they didn't have, and we can say, well, they guessed well. Their assumptions were appropriate in this case because the random intercept really captures the between subject variability, and it also captures the fact that subjects were pretty consistent in the fact that they dropped, right? We're not going to be exact on every subject, but the subjects are pretty consistent in that they all dropped. So just putting in a random intercept was a good choice for the researcher in this data, even though they didn't actually see the 3 lower subjects at visit 2. If we have this kind of situation, this one's hard because the subjects that you didn't see, they had a different pattern than the ones that you did see. So it's going to be hard for the researcher to guess this one, right? Example 2, this is one where you see a change, but the change is related to the starting value. And even though the 3 lower subjects, their slope is a lot lower, if you can predict that their change is going to be associated with that baseline value in a linear fashion, they may be able to guess right and get those predicted changes pretty accurately. So 2 ways of modeling change when it's related to the starting point. We know this, you can do as the outcome, you can put in y2 minus y1. So you're looking, it's a change score model, but you also have Y1 as a predictor. So we called this one the hybrid model early on. That's one way you can do it. You can also fit a linear mixed model by keeping both measures as outcomes and then adding a random intercept and random slope for time. But the problem is if you only have 2 time points, that you may get the mixed model may be a little bit grumpy. You may get an error message or a warning or something like that. But you may be able to get some information from that model, even if you do get a warning. So any questions up to that point? That's sort of just the introduction. What we're going to talk about next are missing data mechanisms. So some of you may be familiar with these terms, but in order to understand how should we account for missing data, you have to have an idea about the missing data mechanism. And what I mean by that is, I'll describe here shortly, but we have 3 basic categories: missing completely at random, missing at random, and missing not at random. Again, statisticians, I think, maybe struggle with finding good terms. This is something that's, just, can cause some misunderstanding, because missing at random, it sounds like what you'd expect is that things are just really missing at random. But when we say missing at random, what in our mind, probably what we really are thinking is missing completely at random. So it's important to really define these terms accurately to understand what they mean. So missing completely at random mathematically is defined as the probability that subject I at time j has a missing value. So m is 1 if it's missing, it's 0 if it's not missing. The probability that m is equal to 1 given the observed outcomes, the missing outcomes, and the covariates is equal to probability m is equal to 1. In other words, it doesn't depend on, the probability that it's missing doesn't depend on the outcome, whether it's observed or missing, or the covariates. So that's truly missing at random. What I would think of as missing at random is really called missing completely at random. So it's as if you have the data set and you randomly go in and remove values, okay? There's a slight variation of that called covariate dependent missing completely at random, which instead of probability m equals 1 on the right side, it's saying that it could depend on the covariates. That missingness could depend on the covariates, but not on the outcome, the observed or missing outcome data. So this is really a type of missing data pattern that is probably not realistic for most data sets, but it's something you can actually test for to make it fairly easy to say for sure if your data follow this type of pattern or not. The next level up is missing at random, which says that the missingness depends on the covariates and the observed outcomes, but not on the missing outcomes. Okay, so for example, and before I get into the example, modeling this type of data can still be done if you have the right variables added to your predictors. So the example is, let's say we have a study where we're looking at progression of lung function over time, and one data set or project that would be relevant here is a COPD gene study that I worked on, and that was actually the talk I had to give right before I rushed back to you guys. So that's a big study, the COPD gene study. That's a multi-center study. There's more than 20 centers involved in this. It's the biggest project I've ever been involved in, and so we're looking at subjects over time, and so we have, for that study, they're actually all either current or former smokers. for the main subjects in the study, they were smokers, but some have quit smoking, and we want to find out, you know, does quitting smoking help you? And we've shown that, you know, compared to those that keep smoking. So let's say that the smokers have lower starting values when we start observing them, and they have steeper drops in response over time compared with the non-smokers. Also, let's say that the smokers are more likely to drop out. So if we have, let's say, 40% dropout over time for the smokers and 20% for the non-smokers, it seems like that might cause a problem. But if you put in smoking status and then smoking status by time, essentially what we're doing is we're then focusing our estimates within groups. And so the missingness depends on smoking status, but by including the relevant predictors, we can accurately model the data. We're not going to be affected by the fact that the dropout rate was different between the smoking and non-smoking groups, because now we're focusing on those specific strata for our estimates.
Do you always have to add an interaction term when you're accounting for this?
I think I would, especially, yeah, I would say that, you know, if the dropout depends on time. So I think it's going to be important to include time by whatever predictor is, you know, for, in this case, it's smoking status, but in your case, it may be a different predictor, but I would definitely start with that model. There might be occasion where you can simplify it, but I definitely would start with it and to see if that interaction is significant in the model. So the last type of mechanism for missing data, or what we call missing not at random, or not missing at random, you might see it either way. And that's when the values of missing data are, the values of the missing data are related to the chance they are missing. So the probability that m is equal to 1, the probability of having a missing value depends on the covariates. It depends on the observed y, and it depends on the missing y. So for example, if subjects, you observe them and then they start to get sick, but then you don't observe that outcome, then that would be an example of missing not at random. And that's the most complicated in terms of trying to adjust for, because, you know, we didn't observe an important outcome that affects the fact that they were missing, right? So the methods that we learned for this type of data, you have to make assumptions, and you have to guess, and you're not really able to check whether it's accurate or not unless you can go back later on and go back and resample those subjects or get more information later. So what's typically done is, you know, we don't necessarily know which type of data mechanism, missingness mechanism, applies for a given data set. So a lot of times what's done is you say, okay, if data are missing completely at random, here's what we'd use, and here's our estimate. If the data are missing at random, here's what we'd use, and here's what our estimate is, and so forth. And you can see the sensitivity of the estimates based on the different assumptions that you make. And what our hope is that those estimates don't change a lot, because then what that's saying is it doesn't really matter what your assumptions were. The estimates are fairly robust to, you know, misspecifications. But, you know, there's going to be some data sets, some messy data sets, where you're going to see a difference, and you may have to use the information you have to try to assess whether, you know, there's one type of mechanism that causes missingness or another. So we're gonna look at some examples here shortly. So the one type of method that I've used for MNAR type of data, missing data, or making that assumption, are called pattern mixture models. So this is the one that I'm familiar with. It's pretty intuitive. There's also selection models. I haven't worked with that one, but I'm going to show you a simple example of a pattern mixture model shortly. And this is what I just mentioned. You know, sometimes you try different approaches and see what the impact on the estimate is going to be. So what we've talked about up to this point is actually missing Y, missing outcome data. What if X is missing? Well, that might require other types of approaches. You could try multiple imputation there. You could try employing the EM algorithm. So there's other approaches that we can consider when X is missing. But what we're going to focus on today is when Y is missing. Okay, so we have enough we have enough to worry about when the outcome is missing, and so that's what we're going to focus on as a first step here. One thing that's true is mixed models are a little bit better than GEE. So linear mixed models compared to GEE. For regular mixed models, you can specify the model and account for missing at random, which is at middle level data. You'll be able to appropriately handle that type of data. Whereas for GEE, you need a stronger assumption of missing completely at random. Okay. I'm going to jump over these slides. I think you can probably just read these couple slides here. And some of this, it would be review as well. I think I mentioned some of these things before. So I'm going to jump over those slides and get to the case study so we can talk about actual data and what we do with it. So some of the examples that we talked about, the ones at the beginning here, we just had 2 time points. And I am going to go back, now that I think about it, there's one thing based on the definitions that we learned: missing completely random, missing at random, not missing at random. I want you to tell me what type of data we have in these examples. Example 1, example 2, that one you probably couldn't include, but let's focus on these 2 examples. Example 1 and example 2. Obviously, we don't know. Again, the thing is, like, the researcher didn't see the 3 subjects that are lower on the graph, right? But looking at the information that we do have, let's say they were able to get that information later. What was the type of missing data mechanism that you think that we had for example 1 and example 2?
Is it not missing at random because it's systematically lower than all the other values?
Yes, I would say that example 1 is missing not at random because the pattern that we saw for the subjects that were missing, that suggests that the missingness depends on the missing Y, right? I would say that, so I would say example 1, this is missing not at random. type of data. Right? Because the missingness depends on the missing y. Okay. What about example 2? This one is not so clear cut, but what would you say here? The question is, can we say that the probability m equals 1 given the covariates, the missing y, and the observed y? Can we say that that's equal to just sorry. Does it just depend on X, stuff that we have? That's really a question. Can we say that the change for the subjects, both the observed and missing, can we find something that we have that will capture that? That's really what the missing at random type of data is saying. So we don't really have covariates for this, right? So we don't have to worry about the X part. But what about the observed Y? Does the observed Y tell us what's going to happen? See Elise nodding her head. Yes, so tell me what you're thinking.
We know that if y is lower, then we know something about the slope to the outcome. But I guess the issue would be, we know that just because we can see ahead.
Exactly. So again, we have the advantage now of saying, okay, now we see everything. What type of data we have. So the researcher at the time wouldn't know it, right? But based on the information we have now, we can say that the missingness, we could see it as missing at random. I would say yes here. So as a question mark, is that true? I would say yes, because, let me see if I can, I'm going to increase this a little bit so I can write more. Because change depends on the starting value. In a systematic fashion. So I would say this is missing at random type data. But again, with missing at random data, the key is you have to put in the information that's going to allow you to do it. So we would have to put in the baseline value, the baseline outcome value. And when we do that, then we're able to get predicted values that make sense. And even though these 3 subjects, their slopes were all higher than the ones that we did observe, by making that correct assumption, we're able to get predicted values that will make sense. Okay, so we know that just by being able to see everything now. Okay, so I'm going to jump back to the actual case studies. All right, so this is, I worked with somebody here at National Jewish, and on subjects that have idiopathic pulmonary fibrosis, and it's an observational study. So we're looking at over time, how is their lung function changing? And another outcome measure that we look at is DLCO, percent of predicted diffusing capacity of the lung for carbon monoxide. And so the higher you can diffuse that, the better. So the higher value indicates a better level of health. And so for subjects that have IPF, you can see a decline in DLCO. But I think you probably remember this data that I showed you. Here is, there's so many subjects. One way of graphing the data is to actually just make a scatter plot and then do an overall average here, right? So weeks from diagnosis. So, we have time 0 here. And so measurements before that would be before they were actually diagnosed. And then you can see most subjects, you start getting a lot more data once they're diagnosed. But the interesting thing is there's kind of a linear pattern, but you see a drop in that function, and then it kind of balances out. And for a while I was like, that's interesting. I better try a spline function to model that, right? Looks like a linear pattern, but if you want to account for that, we could add splines. So that's actually what we did, was we started adding splines. And then I started thinking, well, wait a second. What about the within subject data versus between subject data? What does that look like? That clarifies everything, right? That's a pretty messy plot. And, this is the thing that you have to be careful of when you're going to make a graph. Can you figure out what's going on by the graph? Well, this one's a little bit hard because everything's so tangled up, right? But the thing is, this is an observational study, and subjects may have different amounts of follow-up. And you actually might be able to tell here that there's some of the lines that are dropping quickly for subjects, and then there are others that are continuing on and they're not so steep. So this is my first indication that there's different types of subjects here. And if we just average over everybody, then that may be a convoluted function that doesn't make a lot of sense. So if you stratify on years of follow-up, and you take subjects that had their last observation date less than 100 days from diagnosis and those that were at least 100, you can see the patterns then a little more clearly, that the subjects that had more follow-up didn't drop as steeply compared to the ones that had their last observation date was within a couple years, right? So if we simply average the data over what we have, we end up with that convoluted function. And so we need to tease out what's going on and try to distinguish subjects by the amount of follow-up we had on them. Any questions up to this point with this data? All right, so we'll keep going. So in a nutshell here, what I did was I made 3 different assumptions. I said, let's say the data missing completely at random. Which, do you think that's a good assumption here for the data? I see, yeah, that's the right answer. Definitely no. And why is that? Because subjects that are clearly, like if they're dropping, they're more likely not to come back, if they have a steep drop initially. There's definitely a pattern to the missingness. And so it's definitely not missing completely at random. Is it missing at random? Well, it depends on whether we can find data that can summarize those differences between the subjects that appear to have the early quick drop and the ones that stay in. So it's possible we could find the data that we would need in order to say that this is missing at random. But if we assume that the probability of missingness somehow still depends on the missing Y, then we have missing not at random type data. And under those three different assumptions, this is the slope. We know the slope is going down. If we make this really probably unlikely assumption, our estimate is a 2% drop. I think that's per year. That's our estimate under this assumption. If we assume that we can find the right information in our data, and then and that might even be just adding a random intercept and slope for subjects over time, and that may do it. Then our estimate is about 5% drop per year. And if we do the missing not at random assumption, and I'll use a pattern mixture model, which I'll describe here in a second, we get an estimated change of negative 6.58%. So you can see that we can do pretty well. Like, we don't know which one's the right one, but it's probably more likely missing at random or missing not at random. And we can see that those are somewhat closer, right? And so again, it's kind of like the issue of correlation. If you have a compound symmetric correlation structure, it's probably not good, but it's better than not having anything. If you do missing at random and the data really are missing not at random, it's a lot better to assume that than to just have the really simple missing completely random. So there's levels of how good things are in terms of the type of data you have. Now, again, we don't know which one it is for sure, but at least we know that they're somewhat similar. If we make these one of these two assumptions, that it's probably going to be one of those, right? So the pattern mixture model, what I did here was I basically this was a simple approach where I said there's two patterns. There's the early dropouts and there's the late dropouts. And so essentially what you do is you estimate a function for the early dropouts and the late dropouts, and then you take a weighted average of those if you want to come up with one function. What we actually did in the paper is we just left them separate. We said, for people that drop out early, here's your estimated rate of decline. And if you dropped out later, here's your estimated rate of decline. But if you want to come up with a marginal function, you can take a weighted average of those. You could also look at, you could take this graph and do more than two groups. You could do 4 or 5 and then average those. So that's the point I made here about you could do another approach, and I offered that up as a project for a student when I made these slides out. Okay. I think what I'm going to actually do now is just show you really quickly if I can find it. Just give me a second. There's a really good paper by Hogan, and I think I either have it on the website already, the Canvas site, or I'm going to put it up. But it's a really good paper that gives you the methodology, assuming these different mechanisms, and then applying it. And what I did was And I can post this as well. This is how I came up with those estimates in the table. So missing completely at random, we use a mixed model. And I don't, it's a real basic model where we don't even have a correlation structure in there. And it's oversimplified, but it's a frame of reference that we have. The missing at random assumption we can obtain, in this case, by adding, like I said, a random intercept and a random slope for time. And that gives us that estimate of about 5%. And then the missing not at random approach, we put in time group is the early dropouts versus the late, the subjects that stayed in for a longer period of time. You create a variable for that. That's the new time group. And then you allow an interaction between that and time. And you can obtain your separate regression lines for those. And you can actually, you don't have to use ProcIML here. You could also do some estimate statements to do it. I've been doing that recently. But you can also do ProcIML to obtain a marginal estimate between the groups. So I can post this as well for you guys if you want to use that for your projects. But what we get for this pattern mixture models, here's the function we get for the subjects, the early dropouts, that have a steeper decline in DLCO, and then the function for the subjects to stay in. This brings up a question though, like if we have a marginal estimate, some weighted average of these two, conceptually to me, it's like, I don't know if it makes a lot of sense, especially like early on, I think it's fine. But after, like down here, when these subjects are no longer contributing, should there really be an average out there? I mean, that's just more of a discussion point. But if you feel like you don't want to have a marginal mean, you could actually just report these two separate functions. But this pattern is something you see that's pretty common for longitudinal studies, that subjects that have less follow-up time, they may be on a sharper slope. And if we had more functions to estimate, you might see a similar pattern. So for example, let's say we had 4, the first group might be like this. The second group might be like this. The third group might be like this, and so forth. So subjects that stay in longer tend to be healthier. That's just sort of a natural feature of a lot of data. So I just say health. This is a pattern that you might see, and if you have enough follow-up time, if we have like 10 or 15 points, it's a lot easier in that case to estimate these separate regression lines. And then again, you can come up with one marginal mean function, or you can just say, here's the pattern if you drop out really early, if you have a little bit more follow-up and so forth. But that's something you might notice for your data set. Any questions? Comments?
So is there any way we can just like say one way is better than the other? Do we need to check just like whether our model or the estimator's convergence into certain level? I mean, if we fill up the missing data and then the estimator does not converge anymore, is that means the missing data we filled in it doesn't work?
Oh, are you suggesting like imputation
Um,
when you say fill in the missing data?
Yeah, it's just like how can we just like say this works?
Yeah, I mean that's that's the big question. That's the really good question that, you know, how do we know which one to go with, right? And that's, again, that's the hard thing, because what you really need in order to test the assumption is something we don't have, you know, because we
Yeah.
don't have we didn't observe the data. So I think honestly what you do is you try different approaches, and you can even report different approaches. And I think that's important as well, is to say, well, this is what our estimate would be if we made this assumption. And this is what it'd be if we made this assumption. And so you don't
Yeah.
necessarily have to think that you have to come up with one answer and then not report other things, right?
Yeah.
So there's ways to test between missing completely random versus not missing completely random. We have a test for that, but unfortunately we don't have a test to distinguish missing at random versus not missing at random. And that would be really nice if we had that, but we don't. We don't have the data to answer that question. So a lot of it comes down to what assumptions are you comfortable making? And you may have enough knowledge of your own data to say, I'm comfortable with this assumption. And so I based on the information I do have, I think it's missing at random, or I think it's missing not at random,
So
right? Or you can just say, I'm not really sure, but here are the estimates if you make this assumption. Here's the estimate if you make this assumption. And
so
hopefully they're not too different.
so are we gonna do simulation where like resampling to show that
Yeah, that's
we're
actually a good idea. What you could do, that's a great idea, is simulate data that's similar to the type of data that you have. And then you can run methods using these different assumptions to see which one's closer. That's a good idea. There's another point that was just on the fringe of my mind I was going to say, but I forgot. It'll probably come to me at some point. So I'll follow up with that.
Hey Matt, I have something to
Yeah.
add to that. So I'm working with Katerina and Debashes, and so I've come up with a new methodology for imputation. And so I can actually predict these MNAR and MCAR values before imputing. So I'm kind of finishing this up at the moment with Katerina and Debashes.
Oh, okay. That's good. Yeah, I'm actually going to talk about multiple imputation coming up just briefly. And so that is another method that we have in our toolkit, other than the ones we've talked about so far. Multiple imputation obviously is, that's where you fill in the data, right? You don't have data, you make up values. you fill up your data set, and then you say, all right, I have a full data set, I'm going to see what I get. That sounds kind of questionable, but there's a science to it, right? There's a science. In order to predict the values, you're using information that you do have in order to get a good predictive value. And you do it multiple times in order to account for the uncertainty based on the fact that you're imputing values. So there's a science to it. And there's data sets where that's going to work better than others. It tends to work well if you have a lot of information on subjects and you're just missing a few things. It's going to tend to work better in those cases. But it's a pretty intuitive approach, and I'll be curious to hear more, Jonathan, about what you at some point about what you're doing.
Matt, I'm wondering if you don't impute your Y outcome and you have like serially correlated like time series data or longitudinal data, would that like mess things up if I just eliminated the days, even if they were missing at random, then suddenly you have like 2 days apart in your correlation instead of one? Like I guess maybe a spatially correlated option.
Yeah, so we can overcome that with linear mixed models, with the spatial structure, and if we can tell it, where to find the information about the spacing. So that's usually like in a date or, you know, some kind of time variable that we tell it. For GEE, the way you have to do it is that you actually have to fill out your whole data set, because we don't have spatial structures in GEE. But it'll work, actually. It'll actually work if you have consecutive days or consecutive time points, and you fill in records where things were missing. It's going to work appropriately there.
So is that means we can just ignore them because they didn't provide that much information for our model if they're missing like in the middle of the time?
Well, I think the answer depends on that. I wouldn't say yes or no. I would say I would look at the data set specifically to try to understand. But that you do bring up a good point, Randy, that like in imputation, you have to decide, are you going to impute everything? Are you just going to impute the X, missing X? Because we know, like for mixed models, we can get predicted Y, even if it was missing. So there's some thought behind, you know, how much you're going to impute. If you're just going to impute the covariates, or you're going to impute the covariates and the missing outcome. I would evaluate that on a case-by-case basis.
Yeah, I think that makes sense. If the missing part doesn't contribute that much to the model, we better just leave it out other than just like put some random or like.
Yeah, that's a good thought. That's a good thought. There's this other data set I have. Am I sharing this on my screen? You see this ENO slide? Okay. Just check. So this data set is another one that you guys have seen, where we have subjects that are allergic to aspirin, and so we give them aspirin and see what happens. But in reality, you give them a little bit, right? You want to desensitize their allergic response, and so they have a baseline ENO measurement. ENO is going to, exhaled nitric oxide is going to reflect how much allergic response they're having. So the high value indicates that they're having more of a reaction. And so we take a measurement right before the challenge, and then we give them the aspirin challenge and see what happens to their exhaled nitric oxide. And then we take another measurement 6 months later. And there's a fourth one 1 year after the challenge. So there's a total of 4 we have here. So I just want you to look at the data. Where is it? Here it is. What I did here, we have 21 subjects, and I actually sorted the subjects by their baseline ENO value. And then we can see the information that we have at the time immediately after. We have the 6 months, and then we have the 1 year. So we have, this is the pre-challenge. This is post-challenge. And then this is at 6 months, and this is at 12 months. So we want to follow up and see, were these subjects able to recover from the challenge, you know, over a longer period of time. Now, this is more discussion, like, how would you account for the missing data, and what missing data mechanism seems like it's occurring here? Any thoughts you have when you look at the data and the graph to the right?
So it's missing not at random.
Okay, what makes you say that?
Because your missing values are aggregated to the bottom left of your data points.
Over here?
Mm-hmm.
Yeah, I think at least it's suggesting missing, it's not missing completely at random. There's some pattern to the missingness, right? The higher their exhaled nitric oxide is, you can see that there's a tendency for dropout, more dropout, the higher your baseline is. But the question is, can you find a information, you know, from your observed Y or covariates? And again, we actually don't have covariates, so we're just focusing on missing Y and observed Y. Can you find, so the observed Y, actually you can consider that as a covariate if you put that in as a predictor, right, the baseline value. But the question is, so Jonathan could be right, it could be missing not at random, but it's possible also, if you can find a systematic relationship between the baseline value and what's happening over time, you might actually be able to put in the predictors, you know, put in the observed Y at baseline, and maybe even a function of that in order to account for what's happening. So I would say it could be missing not at random. It could be missing at random if you're able to capture the information you need from that initial ENO value. One concern, and I just noticed this actually, there's only one subject that didn't have the post-challenge value. And I'd be wondering why, like they're there, right? You get the ENO measurement, you have the challenge, they're still there. Why did that subject not? I would be really concerned about that subject. Maybe their ENO went up so much that they had to be treated or something and they couldn't continue. And that would be a concern, although it's only one subject, right? But that would be an example possibly of a missing not at random, where if their ENO went up so high that they couldn't even be measured, that would be definitely a type of missing not at random. But like if you look at this graph on the right, you notice that the reaction tends to get steeper as the baseline value goes up. And that, again, that suggests to me, let's try to figure out if we can use that as a covariate, the starting value. And that might help us. But I definitely would try both. I would try the methods with missing at random, methods with missing not at random, see the impact on the estimates of change. So this is some stuff that I added to the slides recently. So even like if you downloaded the slides before yesterday, this probably wasn't in there. So this was added in. And I'll make sure everything's updated on Canvas as well. So we talked about missing data mechanisms. There's a few others, like if you have missing data, a lot of clinicians that I work with think, well, if we didn't have everything, let's just drop all those subjects out so that we include only subjects that completed everything. And like they think, well, then we get a really clean data set, right? Why is that not not a good idea? Can you guys think of any reasons why that may not be so great?
I mean, it would be great if you were trying to make inference about a very specific type of people who don't drop out from the study, but it's not very generalizable.
Yeah, that's exactly the problem. The question is, who is dropping out, right? Those people that are dropping out could have characteristics that differ from those that are completing, and they could have different trends over time. And so Elise is exactly right. It's good because you're making inference for a group, but it's not generalizable, right? We're just focusing on subjects that have complete cases, and their characteristics could differ from a lot of other people in the data at the start. Last observation carried forward. If you didn't see what they had, just use what they had from the previous time. That doesn't sound great, but it's something that's actually been used a lot. But that's definitely not recommended. All available is where you include information if you have it. And so, for example, in mixed models, we can do this. If you have 5 visits, but they only showed up for 3, you can include them, right? You don't have to have complete case data to fit a mixed model. And that's what I typically try to do. It won't necessarily overcome bias of missing data, but it's at least as good as a complete case. And a lot of times it'll give you more precision because you're including more data. There's a couple new ones, inverse probability weighting and multiple imputation that we talked about a little bit as methods. So the inverse probability weighting is where you take, you do an initial logistic regression and you model whether a subject had observed or missing data at a given time point, and you regress it on a bunch of typically baseline predictors to see, to come up with the probability that a subject's going to be missing a value at a specific time point. So you get these weights from that initial logistic regression, and then you can plug them into the final model to upweight subjects who tended to drop out more, and downweight subjects that tended to be more common, so that you equalize things out. So it's a fairly intuitive approach to handling missing data just by weighting. So you're not imputing data, you're just reweighting records based on whether that type of subject dropped out more or didn't drop out more. One of the tricks with this though is that if you add a weight statement, let's say to proc mixed, then it gets messed up if you have correlation, if you're estimating correlation parameters in there. So you actually have to simplify the correlation structure, use like a VC structure, and then use empirical standard errors to hopefully account for the misspecification of your model. You know it's misspecified because you're not accounting for correlation. But
Does that
again,
apply to all weighting data or just?
say that again, Carrie.
Does that apply to all weighted data or just this inverse probability weighting?
That's a really good question. I think because that issue came up, I've been working with the student on marginal structural models, and we have to kind of use the same approach. And I believe that it can be related to other types of modeling approaches as well. I wouldn't necessarily say yes, it does for sure, but I would say when you use the weight statement, you have to be careful about adding correlation, because then the weights are not going to have the impact that they're supposed to have. So I would say that you need to evaluate it. I don't know of a method to do this other than simulation. Use simulation to figure out if, either including the covariant correlation parameters or not including them. Try those two things and see which one yields a better, more precise estimate, under Monte Carlo simulation. So that's an approach. And if you want to try this with your project, I have a template. I could send you some code if you wanted to try it. Multiple imputation. There's a lot of different types of multiple imputation, and now Jonathan's made another one apparently. But
my method actually isn't multiple imputation.
Oh, okay.
Single imputation method.
What's that?
It's only a single imputation method.
Oh, single imputation.
Mm-hmm.
The multiple is what you're going to do next after the single one, though, right?
Well, we're not sure because it's performing well enough that I might not even need to do a multiple imputation.
Really? Wow. That's interesting. That's like developing a car that, you know, runs on water or something. That's pretty good. I'm very eager to see that now. But there's different multiple imputation procedures depending on assumptions that you're making and whether the missingness is monotone or not. And I'm not going to get into that today, but there's just a variety of multiple imputation procedures that you can apply. But obviously, once you have imputed data sets, then you can fit models more easily, right? But the question is, how good is that imputation? And again, most of them procedures involve multiple imputation. So you impute multiple data sets, and that allows you to incorporate uncertainty in your estimates based on the fact that that you don't have actual values, but you have predicted values in your data set.
So I have a question here. So
Okay.
is that means for what exactly is imputation? Is it like we treat missing data as like some kind of parameter we don't know, and then we just like conditional on that and keep trying until we figure out what's the missing parameter?
Well, what you do is you when you impute so think of a data set where you have some values and then other values aren't there, right? So you're going to put in values where they were missing, and those become values in your data set, but they're not observed values. They're actually predicted values. So we have to account for the fact that they're not real values, even though we have good methods in order to predict them. We still have to treat them a little bit differently than the observed values. And the way we do that is by imputing several times. Now, the multiple is usually like 5. Usually you have 5 data sets, and where each one has imputed values. And then for each of these data sets, you fit the model, right? And so each one, you're going to obtain data estimates for each data set that you have, for each 5 of those. And then based on the variability that you have between those estimates, you can capture uncertainty in the imputation that you did.
So based on my understanding, is that means just like for the missing part of the data, it has like a real information value over there. And each time we try to estimate what's the information part of the missing data.
That's a reasonable way to think about it. Yeah, I mean, really the question is, if you would have had all the data, that's what you're trying to get, right? You're
Yeah.
trying to estimate something as if you actually had the data. So the multiple imputation, you realize that when you put in the values that it may not be perfect, right? But that's exactly the goal, is to try to get estimates as if you would have had all of the data originally.
Okay. Oh, so that's the part. So it's more like based on what we already know, we can find like a weight or like a scale parameter of what the missing data would be based on what we already know based
Yes.
on observation.
Yeah. Yep. That's a good way to put it.
Yeah, thank you.
Yeah. So again, I have some code. If you guys want to try, if you for your project, if you want to try any one of these, okay, now we have 4 or 5 different things that you can try, right? We have basic approaches for if you assume missing at random. I showed you the pattern mixture modeling. If you're assuming it's missing not at random, there's inverse probability weighting, multiple imputation, and I don't have the code here, but I can share that with you if you want to use the inverse weighting approach or the multiple imputation. I can share some code with you if you want to apply it to your data set. I feel like see. I feel like I want to stop. I've been doing so much talking this morning, and I think we also have office hours, right? We may have some more questions. So the rest of the slides, I'll just tell you basically. This shows you some data from the COPD gene study, and just to describe briefly, we have 3 visits or 3 phases. The phase 1 was the baseline, and then subjects came in 5 years later, and then subjects came in 10 years later. And so it's kind of a pretty simple design. We have 3 visits, and we want to see what's happening in different health outcomes over time. So FEV1 is one example. We stratify analyses based on their health at the beginning, and that's one of the reasons or one of the ways that we help account for missingness and dropout that may depend on how healthy your subjects are at the beginning of the study, and that definitely helps. But these slides essentially show you, what you get if you make a missing at random type assumption, or if you make a missing not at random type assumption. And so I think the slides are fairly straightforward. I'll let you guys read those. The last thing I wanted to say is that dropout, what causes dropout? There's different things that cause dropout. Subjects could die, especially, if it's a disease that's very serious and they're older, there may be a higher mortality rate in your study. But there also may be subjects that just decide they don't want to participate anymore, right? And there could be others that maybe are still participating, but they just haven't come back for a visit. They're supposed to come in at 10 years. Maybe they're late. So there could be different reasons for dropout, and you may want to distinguish those things. You may want to treat somebody who died differently than somebody that dropped out. And so that's just kind of a food for thought comment I want to make. And we can talk about it more. If this applies to your study, we can talk more about it, because the way you treat, subject that died, maybe that shouldn't be the same as a subject who's alive, and that you could have actually gotten a measurement if they would have stayed in the study. So that's just something to think about. And again, if anyone, for your project, if you have any specific questions about how to apply missing data methods, I'd be happy to talk to you about that. I've talked to probably 5 or 6 people. And before I forget, Jonathan and Wei Shan, is that how you say your name?
Yes.
I got the green light from Karen. I'll send you the paper that she did on spatial temporal modeling. I'll send to you guys, and I will also post some other sample papers for you guys to look at, so that you have an idea about how to shape your project paper.
Okay. Thank you.
Yeah. So it's about 10. If you give me like 10 minutes, I'll stop the recording here. But I'd say like 10:50. Give me till 10:50, and then I'll be back for office hours if people have questions. Sound good? Okay. All right. See you in a bit.